Hello and welcome back to another Orange Coast College mathematics video. In this video, we are going to be talking more about polar coordinates, specifically polar equations. So just as in the Cartesian coordinate plane with the x's and y's, we can have an equation that represents a collection of points. We have that case in polar as well. So I'm going to do a little bit of conversion here. In this first problem, it says to give the equivalent polar equation. Well, I'm going to note first that x squared plus y squared perfectly matches up with this x squared plus y squared. So I can substitute that in and say this is the same thing as r squared is equal to 4, which of course means that r is equal to 2 or negative 2. If r is equal to 2 or negative 2, remember, what does that really mean? Well, it's saying that you have a constant radius. The radius is always 2. And if you always have a constant radius of 2, that's exactly what it means to be a circle. And of course, this is the equation of a circle of radius 2 in the um, in the Cartesian coordinate plane. So we get a circle of radius 2, which is the same thing with negative 2, because having a constant radius of negative 2 just means you're going in the opposite direction, but you're still really getting the same circle. So you can write it either way. Usually we'll go with a positive radius, and this is what the graph looks like. Now for this guy, you know from your algebra class or from the algebra videos that this is the equation of a line. The line has a slope-intercept of 1, 2, or sorry, a y-intercept of 2. If I plug in 0 in for y, I can find the x-intercept. So that means I get 3x is equal to 2, and therefore x is equal to 2/3, which is going to be right about here then. And so I get a line that looks something like this. So of course this is the equation of a line. What more? Well, I want to set this in terms of polar coordinates, or polar, right, as a polar equation. So let's remind ourselves that we know that x is equal to r cosine of theta and y is equal to r sine of theta from the last video. We also see we've got them written right here. Using this substitution, I'm going to recognize a couple things. The first is that I'm going to plug in for what y and x are into this equation. So I'm going to get r sine of theta is equal to negative 3 r cosine of theta plus 2. So now we actually are in terms of polar coordinates. We typically like to solve for r in polar coordinates in the same way that we like to solve for y in Cartesian. So I'm going to go ahead and add the 3r cosine of theta to both sides to get r sine of theta plus 3r cosine of theta is equal to 2, and factor out an r from that. And if I divide by everything but the r, I get r is equal to 2 over sine of theta plus 3 cosine of theta. Now, and that's our answer, but I'll make a comment. Notice that in this first example, I think the Cartesian, or the polar equation, is probably a little bit nicer. You can't get much simpler than r equals 2. But for the linear equation, I think it's probably nicer in Cartesian form. And so the point is, sometimes it's easier to work in polar coordinates, and sometimes it's easier to work in Cartesian coordinates, and that carries through to throughout mathematics and calculus and beyond. Is you use the coordinate system that makes sense, that makes the computation and the mathematics you're trying to do easier on you. So let's go ahead and continue. In this next example, we are given polar equations and we want to write an equivalent one in rectangular coordinates and in graph. So if I'm trying to convert this guy into Cartesian, I'm going to multiply it by an r. And the reason I'm thinking that that might be a good idea is two things. One is I know what r squared is equal to. From the Pythagorean theorem, I know it's equal to x squared plus y squared. But I also know this r sine theta is going to be y. And so I'm getting this into a form that's going to allow me to substitute. This r squared is x squared plus y squared. This r sine theta is really just y. And now we have an equation that is in terms of x and y's, which is a perfectly valid form for an equation. But to really see what's going on here, I'm going to do a bit more. I'm going to subtract the 8y from both sides. I'm going to complete the square, which you've seen in your quadratics video, by adding half of this term squared to both sides. X squared plus y squared minus 8y. I'm going to add 16 to each side, because that's going to make this factor into a perfect square. X squared plus y minus 4 squared is equal to 16. And in this form, it becomes clear what I'm dealing with. I have a circle centered at the point 0, up 1, 2, 3, 4, with a radius of 4. So 16 squared is 4. So I'm going to be off the page here a little bit. That's okay. Better circle than that needed. And so I'm getting a circle of radius 4. And so I get something that looks a little bit like that. So this is really a circle of radius 4. Moving on to the next problem, going to do the same kind of thing. I'm going to multiply by an r through. Get r squared is equal to negative 4r cosine of theta, which means I'm going to get x squared plus y squared is equal to negative 4x. Adding that 4x over, I'm going to add 4 to both sides, completing the square here, and get x squared plus 4x plus 4 plus y squared is equal to 4, which means x plus 2 squared plus y squared equals 2 squared. So I have now a circle again at centered at negative 2 comma 0 with a radius of 2. And so I get a circle that looks a little bit like this, centered at the point negative 2, 0 with a radius of 2. Now this last guy is 5 cosecant of theta. I'm going to use the fact that this is the same thing as 1 over sine of theta. And the reason I'm going to do that is because I can now multiply by sine of theta to both sides and get r sine of theta equals 5. But what's r sine of theta? R sine of theta is just y. So this is really y is equal to 5. And so r equals 5 cosecant of theta in polar coordinates is actually just another way of saying the horizontal line y is equal to 5. And that will conclude this video on polar equations.